We've already seen the long exact sequence of a pair of spaces, and we will now discuss a long exact sequence associated with a triple of spaces. So the lemma, which has a more technical nature, is the following. Let X be a space, and let A and B subspaces. A lies in B, and B is in X. And then there is a natural long exact sequence called the triple sequence, which goes from Hn plus 1 x, a to Hn plus 1 x, b, induced by the inclusion, and then a boundary operator which we have to define to Hn b, a, Hn x, a, and so on and so forth. And we have this boundary operator that we have to define here, and all the other maps are induced by inclusions of pairs, the obvious inclusions of pairs. So let's prove this.
And as opposed to excision, this time there's no requirement on the topology, nothing with interior
just subspaces, don't have to be open or anything like that.
For the pair sequence, no requirement.
So we have to define, as part of proving this lemma, the boundary homomorphism. Which goes from Hn plus 1, sorry. If I write dn, I should write Hn x, b to Hn minus 1 b, a. And we define this as the composition of a boundary homomorphism in a long exact sequence associated with a pair and the inclusion map. So we define it as the composition going from Hn x, b via the usual boundary operator for the long exact sequence belonging to the pair x, b. So this goes to Hn minus 1b, and then we just take the inclusion. So if you want the pair B empty set being included into BA, and that's the boundary homomorphism. Now we have to prove that two successive maps composed give the zero map, and moreover that the kernel is really exactly the image in this long exact sequence. So let's first prove that composing two maps, successive maps in this sequence really give us the zero map. And let's first look at this composition. So Hn b, a to Hn x, a, and then Hn x, b. So this is, it's not completely here. So here at this spot, Hn ba, it's not really visible, right? So here. If we start from here at this spot and go further 2 arrows, then this gives 0. So this is the statement here. So we have to show this is the zero map. And here we just have the maps induced by inclusion. Why is it the zero map? Well, because it factors over Hn b, b. So also here we have the maps induced by inclusion. On the space level, this diagram commutes, but we already know that this is 0 for all n. And this proves that this composition is 0. Now I want to look at the composition of the two errors that we see here. So first the boundary homomorphism, and then this map induced by inclusion. For that, I look at the following diagram. So we have here hn x comma b, here hn minus 1b comma a. Here we have this boundary homomorphism that we defined, and here we have x comma b and the inclusion. Okay, so I want to show that this inclusion here, sorry, not this inclusion, this composition here is the 0 map. And to see that, we complete this to a diagram where we have here hn minus 1 of a, and here we have the boundary homomorphism of the sequence associated with the pair x comma a. Here we have hn minus 1b, also with the boundary homomorphism associated with the pair x comma b. Here is the map induced by inclusion. This square commutes by the naturality of the boundary homomorphisms. And here we have also the map induced by inclusion. And by definition of the boundary operator here, this commutes. That was the way we defined it. So we want to show that this here is 0. Why is it 0? Well, we can go like that and then follow the diagram on the bottom. But on the bottom, we have two successive homomorphisms in the long exact sequence of the pair b comma a, and this is 0, and therefore the whole thing is 0. Okay, so this here is 0 because it appears in the long exact sequence of the pair b comma a. There is a third case we have to consider for the composition of two maps to be 0, but this I leave as an exercise, goes in a similar way. What we have achieved so far then is that the image at each spot of this sequence lies in the kernel. Now we have to show that it's really exact, that also every element in the kernel is in the image of the previous map in the exact, in the triple sequence. It is another opportunity to practice our skills in a diagram chase. The diagram has a funny form. It's a so-called braid diagram. I want to show the proof of exactness, so the fact that the kernel equals the image at one spot in the triple sequence. And I want to show it and demonstrate it at the spot hn x comma b. And to do that, we use a diagram which has the form of a braid diagram. And in that diagram, which commutes, you see a lot of excerpts from long exact sequences of pairs. So first of all, you see here the long exact sequence, or part of the long exact sequence of the pair b comma a. Here you see it for the pair x comma a, and here on the right you see it the start of the or part of the long exact sequence of x comma b. And these sequences, these parts are interwoven as braids. And we also see the triple sequence, or part of the triple sequence in the diagram. If you look at here, and then you go down like that, to here, you see this triple sequence. Now I want to show the exactness of this triple sequence at this spot. So we have to take an element here that maps to 0 in hn minus 1 b comma a. So let's say this is sent to 0. And now let's utilize our skills in diagram chasing. The definition, the very definition of this differential was this composition. And we can map this element to an element here, and this element is then mapped to 0. Here. Now, this element here can certainly be mapped further to here, but then it will be mapped to 0 just because what you see here is part of this long exact sequence of the pair x, b. So this is mapped to 0 here. The fact that this element is mapped to 0 down here tells us that it is actually coming from Hn minus 1a because of the exactness of the sequence associated with the pair b, a. So there is not a unique element, but there is certainly an element here that is mapped to this element. And since the whole thing commutes, it is mapped to 0 here. Now I want to use the exactness of the sequence of x, a, which we see here. So this is mapped to 0, meaning that it comes from here. All right. So now you might have forgot what we really want to show. We wanted to show that if an element here is being mapped to 0, it comes from here in the triple sequence, right? What we have gained so far is an element in Hn x, a, so that's the first candidate for a pre-image of that element. But now we have a similar phenomenon that we encountered in the proof of the 5 lemma, that the very first candidate might not be the right one, but we can correct it. And this is what's happening here, because we know that this element is mapped to that element, and if we map it down here, we don't know that it's mapped to this element we started with, but if we map it further to Hn minus 1b, it is mapped to the same blue element here. And that's all we know. So let's map it down there, but let's give it now the image a different color. So we have this blue element we started with, for which we wanted to find a pre-image in Hn x, a, and we have this red element that has a pre-image in Hn x, a, but blue is not necessarily red. What we do know is that the difference of this blue and the red element is being mapped to the same element in Hn minus 1b.
Well, the difference is sent to 0.
The difference, oh yeah, sorry. Yeah, the blue element and the red element are being mapped to the same, so the difference of blue and red is mapped to 0. So we have an element that is being mapped to 0 here. And now I'm a bit short because we have already gained some experience in diagram chasing. The difference is somehow the correction term, okay? If we find a pre-image of the difference of the difference or blue element minus red element, if we know that blue minus red comes from Hn x, a, no, which one? Is it blue minus red or is it red minus?
I don't know.
No, it's red minus blue. It's red minus blue. We have to look at red minus blue. If red minus blue comes from Hn x, a, all right, then we take this pre-image of red minus blue and add it to that blue element, giving us a new element in Hn x, a, but that element is then mapped to the blue element we started with, and we're done. So we look at the difference, red minus blue, which is being mapped to 0 here. But if it's mapped to 0 here, then it comes from here, because that's a long exact sequence of the pair x, b. So the difference, red minus blue, comes from here. All right, but then we can map that pre-image of red minus blue to Hn x, a, and then this gets mapped to red minus blue. So red minus blue has a pre-image in Hn x, a, and that's exactly the correction term that we have to add to this blue element here to get a new element in Hn x, a that then really gets mapped to the element that we started with. And that's the exactness of Hn x, b. And the exactness at the other spots follows a similar argumentation.